Hello students, welcome to this lecture on the subject of advanced semiconductor devices KEC 056. This is lecture number 14. I am Dr. Raman Kapoor, Associate Professor at ABES Engineering College, Ghaziabad. In today's lecture, we are going to study what is known as terminal functions in PN junctions. Okay. When we say terminal functions, we are basically referring to how you can modify a PN junction via doping or biasing or any other means, so that it can be used to produce different functions. Okay. So, let us start. Terminal functions, by the name itself, we know that a PN junction is a two terminal device. Okay. So, it will have a terminal at its P edge to access the P type semiconductor. It will have a terminal on the N side to access the N type of the semiconductor. It can be used to perform various terminal functions depending upon how you have doped the P and N side, depending upon how you have constructed it, depending upon what type of biasing you apply to it. Okay. So, you can alter the doping profile. So, that is going to affect the electrostatics of the depletion region. The built in potential increases with increase in doping, depletion region width reduces with increase in doping, electric field at the junction increases with increase in doping. So, these electrostatics are all doping dependent. When you apply forward bias, you reduce the width of depletion region, you reduce the potential barrier across the junction. When you apply reverse bias, you increase the width of the depletion region and you increase the built in potential across the junction. Okay. So, the terminal functions of a PN junction can be segregated on the basis of its IV characteristics, CV characteristics and breakdown behavior. Okay. So, the aim and objective of today's lecture is to study various terminal functions which a PN junction can implement or execute. Okay. So, let us start with the first one. Many of you would know that a PN junction diode can be used as what is known as a rectifier. Okay. A rectifier is nothing but, well, if it is used by a PN junction diode, it is also going to be a two terminal device. It gives very low resistance to current flow in one direction and very high resistance in the other direction. So, a rectifier is also a sort of a switch, and we know that a PN junction diode also acts as a switch. An ideal diode, if I draw the symbol of a diode here and I say that this diode is ideal. Okay. If this is an ideal diode, I would say that it is acting like an ideal switch. An ideal switch, the IV characteristics will be very high current at forward and 0 current at reverse bias. Okay. So, this is how the characteristic of an ideal switch should look like, which basically means 0 resistance in forward bias and infinite resistance on the reverse bias. Practically, if you can get something like this, this is very close to a practical switch. So, very low forward resistance and very high reverse resistance, okay, which basically can be obtained from a diode. So, that means a diode can be used as a rectifier also. Okay. Because a rectifier is required to conduct only in one direction and your diode only conducts in forward direction. So, this is a very good mapping of application, right, of a PN junction diode as a rectifier. The forward and reverse resistances, whether it is a rectifier or a normal PN junction, they can be obtained from the IV characteristic. Okay. Because if you have the IV characteristic, the slope helps you to calculate resistance, right. So, the diode IV equation or the Shockley equation, we have already derived it, is given as I equal to I naught exponential V by eta Vt minus 1. Okay. This term eta might be new to you. Eta is known as, or I should write here, eta in this IV characteristic is known as ideality factor. Okay. This factor basically measures how close the IV characteristic of a practical diode is equal to its ideal characteristics. Okay. So, I have drawn the IV characteristic of ideal diode on the previous slide and also shown you the practical characteristic. How close the practical characteristics resemble that of an ideal diode, that basically says or shows what is the value of ideality factor is. If the current is dominated by diffusion, ideality factor would remain as 1. If by recombination, it will remain as 2. Okay. So, ideality factor generally fluctuates between 1 and 2. For silicon diode, it is different. For germanium diode also it is different. So, it is also material dependent. It is dependent upon the current mechanism also. Okay. The static and dynamic forward resistance. Whenever I say forward resistance, I mean the resistance offered by the diode when I have applied forward bias to it. So, if I connect P electrode to positive terminal of the battery and N terminal to the negative electrode of the battery, I have forward biased the PN junction. During this biasing, whatever resistance it is offering, the diode is offering, that resistance is known as the forward resistance. Okay. Now, this can be either static or dynamic. Whenever we say static resistance, that is the resistance which you have generally measured at any given one single point on the IV characteristic. If you incorporate the slope of the IV characteristic, what we measure is known as the dynamic resistance. So, static forward resistance is defined as the ratio of forward voltage across the diode divided by the forward current flowing through the diode. Okay. So, Vf by I naught, and whenever I am saying If, it means the applied voltage is positive. Okay. So, V is positive. V is positive in forward bias. When V is positive, the exponential term is very large as compared to 1. So, this 1 can be ignored. Okay. So, then in forward bias, when forward current flows, If is nearly equal to I naught exponential of V over eta times Vt. Okay. This is the forward resistance. If Vf increases, there is a minus sign here, Rf is going to go down. So, forward resistance is going to be a low value in forward bias. Slope is the derivative of dVf by dIf. So, reciprocal of the slope of IV curve in forward bias is your dynamic forward resistance. Okay. So, this equation, if this is Vf, if I differentiate this, I am going to end up with this term. Okay. I suggest you do it yourself also. So, this is going to be the dynamic forward resistance. Similarly, I can do the analysis during reverse bias also. The static and dynamic reverse resistance, this is the resistance offered by the diode when I have applied a reverse bias to it. Okay. Now, because current flows very less, the magnitude of reverse current is very less, it is safe to say that the reverse current is generally of the order of microampere and forward current is of the order of milliampere. Okay. To see the distinctness of the switching behavior. So, reverse resistance, static reverse resistance is defined as the ratio of reverse voltage across the diode divided by reverse current flowing through the diode. Okay. If I go back to the IV equation, when V is negative during reverse bias, this is exponential term. So, this term is very less as compared to 1. So, now I will ignore the exponential term. So, I is nearly equal to minus I naught reverse saturation current during reverse bias. Okay. So, this is my reverse resistance, static one. Dynamic defined as derivative of dVr by dIr. Okay. So, IR is basically minus I naught. Okay. So, dVr by dIr is obtained as this expression here. Okay. Vr by eta Pt minus 1. Okay. So, this is the curve which you are going to get, or the expression you are going to get for dynamic reverse resistance. If the magnitude of V r goes up, there is no negative sign here, there is a plus sign here. If V r goes up, dynamic resistance is going to go up. So, high resistance during reverse bias, low resistance during forward bias. The rectification ratio is defined as the ratio of reverse resistance to forward resistance. So, the rectification ratio can also be static and dynamic. You divide the static reverse resistance by the static forward resistance, static rectification ratio. Same for dynamic rectification ratio. Okay. So, this is going to give you the switching behavior of a diode which can be used to obtain a rectifier. Okay. The rectification ratio DC or static, AC or dynamic is given by these expressions here. Okay. PN junction rectifiers generally have slow switching speeds. So, the time it takes to switch from forward to reverse and reverse to forward is actually large. Okay. So, significant time delay is necessary to obtain high impedance after switching from the forward conduction to the reverse blocking state. This time delay is proportional to the minority carrier lifetime. Majority of rectifiers can dissipate small amounts of power 0.1 to 10 watt, exhibit reverse breakdown voltages from 50 to 2500 and switching times from 50 to 500 nanoseconds. Okay. Another terminal function of a diode can be in voltage regulation, which is generally done via a Zener diode. If I want to simply compare a Zener diode with a standard PN junction diode, a Zener diode is obtained when you have very high doping on the P side and the N side. A standard PN junction diode will only have moderate levels of doping on the P side and the N side. If the level of doping is excessively increased on both the sides, you will have a very thin junction, very thin depletion region. The width of depletion region on P side and N side will be small. The electric field at the junction is going to be very high. When you apply reverse bias to a Zener diode, the minority electrons in P side and the minority holes in the N side, they find support from this electric field at the junction, because the direction of this depletion region electric field is from N side to the P side. Holes are minority in the N side, electrons are minority in the P side. Holes move from positive to negative, holes move from N to P in reverse bias. Direction of this electric field is from N to P as well. So, this electric field supports the minority charge carriers which constitute current during reverse bias, and since doping is very high, this electric field is very high. So, the breakdown of the junction, the reverse breakdown of the PN junction is going to occur at small breakdown voltages, and this behavior can be used to produce a voltage regulator or a Zener regulator. After breakdown, the resistance offered by Zener diode is very small. So, the voltage across it remains fairly constant. Any excessive current is absorbed by Zener current after breakdown, because its resistance is very low. Ideally, the resistance of a Zener diode after breakdown is going to be 0. Ideally, the resistance of a Zener diode before breakdown is going to be infinite. Practically, the change in resistance, reverse resistance of a Zener diode before and after breakdown is very distinct. Very high resistance before breakdown, very low resistance after breakdown. So, this Zener diode, if you connected in a circuit similar to this, okay, this is the symbol of a Zener diode. So, if you apply positive to the N side and negative to the P side, this is a series resistance. If I connect this Zener diode in parallel to a load, this load will experience same voltage as the Zener diode because they are in parallel. If any excessive current enters this circuit, it is going to be absorbed by Zener diode and your load will be saved, or it will be regulated. Okay. So, this is one of a major terminal function of a Zener diode, to be used as a voltage regulator. Most Zener diodes are made up of silicon due to its low saturation current and also because silicon has very advanced fabrication techniques. These are special p-n junction, as I have said, they have very high doping on either side. They do not experience avalanche breakdown because avalanche breakdown happens for low doping cases. For doping for breakdown voltages higher than 6 Eg by Q and temperature coefficient is positive. Band to band tunneling dominates for breakdown voltage less than 4 Eg by Q and temperature coefficient is negative. So, a voltage regulator based on this information would be undergoing band to band tunneling. Breakdown voltages of a Zener diode as compared to a standard p-n diode will be lower in magnitude. If you want to design a temperature insensitive voltage regulator, you can connect a diode with negative temperature coefficient in series with that of a positive temperature coefficient. So, a Zener diode in parallel with a standard p-n diode where avalanche mechanism dominates, this can produce a voltage regulator which is temperature insensitive. Okay. Another terminal function is what is known as a varistor. Now, I am talking about throughout this lecture I am talking about various application where you can use p-n junction. In one of my initial discussion I had said do not consider p-n junction as a normal 2 terminal diode, consider it as a building block for many other devices. Many devices and circuit will have p-n junction inherently present. Whatever electrostatic is associated with a p-n junction, that is going to dominate the behavior of that particular device. Okay. So, we have seen one device like rectifier which exploits the switching behavior of a p-n junction. We have seen Zener diode which exploits the electrostatics of a p-n junction with high doping. Okay. Next we are discussing is what is known as a varistor. Varistor is a word made up of two separate words, variable and resistor. Okay. It is again a 2 terminal device that shows non-ohmic behavior. Now, it is a resistor, a variable resistor nonetheless, but it is showing a non-ohmic behavior. Okay. So, it is not following Ohm's law per se, it is a voltage dependent resistance. The forward biased p-n junction diode exhibits such non-ohmic characteristics. Why? If you remember Ohm's law V equal to I R, if I want to study Ohm's law or obtain the value of resistance of a resistor, the IV curve is going to have a linear slope of 45 degrees. And if I take the slope of this curve, the reciprocal of the slope is going to give me the value of R. Compare it with the forward biased characteristics of a p-n junction diode. It looks something like this. This is no way comparable to this. Okay. So, this is non-linear, but it offers forward resistance also, right, which means it can be used a diode a 2 terminal p-n junction in forward bias can be used as a voltage dependent resistance or a varistor. Similarly, you can also use metal semiconductor contacts. These type of contacts we are going to discuss in next 1 or 2 lectures also. They can also be used for showing these non-ohmic behavior. Varistor have an interesting application. They can be used as symmetrical fractional voltage limiter if you connect 2 diodes in parallel and they are oppositely poled. So, one is forward biased, another is reverse biased. The 2 diode unit will exhibit the forward IV characteristics in either direction. Okay. So, in one direction one is forward biased, in another direction another is forward biased. So, at least one is always forward biased. Being a non-linear device, it is also useful in things like microwave modulation, mixing and demodulation. Varistors based on metal semiconductor contacts are actually more common because their switching times are very less. Okay. Why their switching speed is higher, we are going to discuss very soon later on. Okay. Another terminal function of a p-n junction is what is known as varactor. In a very recent lecture, I had discussed about diode capacitance. When you reverse bias a p-n junction, you increase the width of depletion region. This is similar to a parallel plate capacitor where you have a p type plate and an n type plate separated by a dielectric known as depletion region. The capacitance offered by this reverse biased p-n junction is known as transition capacitance, which is generally measured per unit area and given by this expression epsilon s by W d. W d is nothing but your depletion region width. Okay. Generally, this can be used in your tuning circuits or resonant circuits. Say you have an LC resonant circuit, generally having a variable inductor is very difficult. Integrating an inductance on an IC is also very difficult. So, one would say that inductors should be fixed, value of inductance should be fixed, and if you want a variable resonant frequency, the resonant frequency is given by 1 by 2 pi square root of L C. If I keep L constant and vary C, if this C is variable, your resonant frequency can also be made variable. Okay. This kind of an application finds use in things like harmonic generation, parametric amplification, mixing, detection, voltage variable tuning. Okay. What I have just shown you here is this is voltage variable tuning. Okay. If I increase reverse bias, the width of depletion region is going to increase, which means CT is going to go down. The opposite is also true. If I reduce the magnitude of reverse bias, depletion region width goes down, transition capacitance increases. Either way, the resonant frequency changes. Okay. So, what I am doing, I am making the reverse voltage variable and I am altering the frequency of a tuning circuit. This is what the basis of a varactor diode is or varicap diode is, variable capacitance diode. Okay. So, a diode in p-n junction biased in reverse bias can be used as a voltage variable frequency tuning circuit. Okay. Another terminal function is what is known as a fast recovery diodes. These are designed to give ultra high switching speed. In the transient analysis, we have seen that whenever you switch from forward to reverse, that is the thing, that is the transition which takes lot of time. First there is constant current time, then there is current decay time. Okay. These are classified either in the category of p-n junction or metal semiconductor junction diodes. Total recovery time T1 plus T2, T1 is your constant current time, T2 is your decay time. These can be substantially reduced if you introduce things like recombination centers, like deliberate gold impurities in silicon. Gold will act as recombination center, it will reduce your carrier lifetime. Okay. However, there is a trade off here, your reverse generation current also increases if you increase the number of recombination centers. Okay. So, there is a sort of a trade off, you have to find an optimum scenario, right. So, this kind of scenario is this kind of terminal function is known as a fast recovery diode. In direct band gap semiconductors like gallium arsenide, these are your semiconductors where electron have same momentum at EC and EV. So, when electrons recombine in these semiconductors, they emit light instead of heat, the basis of your LEDs. Here the minority carrier lifetime are generally smaller than that of silicon. So, this results in high switching speeds and recovery time which is very less, of the order of 1/10 of a nanosecond. For silicon diodes, the practical recovery time can be up to 5 nanosecond also. So, switching is slow. Okay. Schottky diodes, the so called metal semiconductor junction diodes, they have very high switching characteristics, okay, because they are sort of unipolar, they only have one type of semiconductor. Okay. Another terminal function is what is known as charge storage diode. By the name itself, you can say that it is storing charge, it is designed to store charge while conducting in forward direction, and when you switch it to reverse direction, it conduct a reverse current for a very short period of time and then the reverse current goes to 0. Typical example is what is known as step recovery diode or a snapback diode that conducts in the reverse direction for a short period and then abruptly cuts off current as the stored charge has been used. For realizing this charge storage action, it is desirable that you reduce the decay phase or T2 without without reducing the constant current phase time T1. Okay. Most of these diodes have relatively long minority carrier lifetime, which ranges from half to 5 picoseconds. Such lifetimes are usually 1000 times longer as compared with fast recovery diode. The mechanism by which you can reduce your decay phase is to have a special doping profile such that injected charge is confined closer to the region close to the junction. This cutoff occurs in the range of picosecond and then eventually results fast rising wavefront, which is rich in harmonics. So, it can be used for things like harmonic generation, pulse shaping. Okay. Next terminal function which I want to discuss, which is very frequently used in high frequency microwave circuit, is what is a pin diode. I here stands for intrinsic. So, between P and N type semiconductor you sandwich an intrinsic region. Intrinsic is the region which is not doped at all. Okay. So, the idealized intrinsic region, you can either have a high resistivity P layer known as pi layer or a high resistivity N layer also known as nu layer. Okay. So, in your P and N region, you have a P and N region and you sandwich a intrinsic region in the middle. This is known as a pin diode. These are widely used in microwave circuits. They exhibit low and constant capacitance and very high breakdown voltage. Used as a variable attenuator because they can control the device resistance, which varies approximately linearly with the forward biased current. At a very high frequency, it is a pure resistor. So, you can say that it is frequency dependent. It has multiple applications in microwave area. Okay. So, these are some of the references you can refer to. What we have covered in this lecture is major terminal functions of a PN junction like rectifiers, voltage regulators or variable capacitance tuning circuits or variable resistor circuits or pin diodes for microwave application, which basically means that PN junction can form as a basis for major other semiconductor devices or advanced semiconductor devices. We will continue our discussion from next lecture. Thank you for now.